Hello and good day, geometry. I better start on page 1 here. Looking at math packet 11 with you today. This is your second to last math packet of the year for geometry. It is due May 4th. And let's just dive right in. So a solid gold pipe is cut into 2 equal parts. One of these parts is shipped to Boston. Don't know why. 3/4 of the remaining half is cut into 9 equal parts. You purchased one of those 9 parts for $55.55. What fraction of the original pipe does your part represent? So basically, what I'm asking you to do here is, draw a bar to represent this pipe and essentially do what the question says. Divide it into 2 equal parts, ship one of those to Boston, and then take the remaining half and divide it into 1/4 and 3/4 sections. And then in the 3/4 section, divide that into 9 equal parts. And essentially the question is asking is, what fraction of the original pipe does one of those 9 pieces represent? And so if you draw it out, you kind of model it, you cut a bar in half, and kind of do what the question says, your fraction sense should kick in to be able to answer the question. But really, this line doesn't matter at all. This line doesn't matter at all. That's just extra stuff. So you can take it from there. The next one. There are 4 towns, A, B, C, and D, positioned on the vertices of a perfect square with side lengths of 1 mile. So if we were to connect these towns in a square-like fashion, okay, we'd have a perfect square with side lengths of 1 all the way around. You want to connect them together by roads. Building roads is very expensive. In fact, it's $2,150 per mile. So you need to be sure to minimize the amount of roads needed. What is the cost of the cheapest road design you can build that will provide a way to drive to each of the 4 towns? Okay, you are looking for the minimum distance of roads that allows you to drive to each of the 4 towns. Not connect all the towns to each other, like not a direct route from B to A and B to D and B to C, but just the least amount of roads necessary that will allow you to drive to all 4 towns. Okay, I'll give you a hint. This is not the answer. A simple square is not the answer. We just finished up a unit on squares, so kind of think about the different characteristics, different properties of a square, and the least amount of roads. And what is the cost? The ultimate question is what is the cost? Okay. Next one, 5-card challenge. We've talked about this before. Make sure you get one equation using all 5 cards. You need at least 21 points, and you're trying to make a 10 with the 5 cards that are given. This one, the shaded area, it didn't copy off so well with the shaded section, so I had to kind of draw it in myself. So it's the entire trapezoid here, not just the part that I have shaded, but it's the entire trapezoid. And this is a look back at Pythagorean theorem and sine, cosine, tangent, as well as your knowledge of trapezoids. So some things to point out here. I tried not to cover it up. This is a 6. That 6 is the height of the trapezoid. Okay, and then using Pythagorean theorem and sine, cosine, tangent, the trick to this one, so to speak, is to get the length of the other base of that trapezoid, because once you get that base, you're given the top base of 21, and you plug those things into the area for a trapezoid formula, which is 1/2 times the sum of the bases, which is why that bottom base matters, times the height. Okay, got some right triangles to work with there, and Pythagorean theorem and sine, cosine, tangent, pretty much what you were after. Next one, the pattern question. We talked about this in algebra, and you are doing another formula, not a graph this time. So complete the table and then write 3 expressions. 1 telling me the number of green blocks for the nth figure, 1 telling me the number of blue blocks for the nth figure, and then the number of total blocks for the nth figure. Okay, such that if I ask, how many green blocks are in figure 29? All you need to do is plug in 29 into your formula, and that's going to give me the answer directly. Okay, so I'm not looking for what is the pattern necessarily. You should not need to know how many blocks are in figure 28 to tell me how many blocks are in figure 29 based on the use of your formula. So those that have asked for help in the past, I said make a function table, make an XY table with the figure number being the X value and the total blocks, or the blue blocks, the green blocks, or whatever you're solving for, be the Y. So you've got a formula that gets directly from the figure number to the number of blocks. Next page, the figure below is the rectangle of the prism. Answer the questions for your class, show your work. You do need to draw a net, don't forget about that, and label all of its sides. And for geometry here, it says, given that the surface area is 258 square units, find the value of x. So like we talked about in algebra, where you have to find the volume, or you're given the volume here, you want to set up an equation. Okay, when in doubt, set up a relationship, and an equation is a relationship. So what do we know? Well, we know that the surface area is the area of all the sides, all the faces, added together. So if we know the surface area is 258, that 258 is going to be equal to the area of each face added up. The top and bottom faces, where we're given the 5 and given the 9, we know each of those are 45. Excuse me, I had to sneeze there, so I turned off the microphone. At least I hope I did. So 45 and 45 there. But beyond that, things get a little bit trickier with that x minus 1. We've got the front and the back faces, which both have an area of 5 times x minus 1 and 5 times x minus 1. I meant to write that in blue. Let me write that in blue again here so we can follow along. 5 times x minus 1, oh my, plus 5 times x minus 1. And then we have a third set of faces, which is the kind of the I don't know, the two sides, the right and the left here, so to speak. And those each have an area of 9 times x minus 1. So look at that equation that you get to solve there. But once you get that relationship written down, it's just the algebra. You've got some distributing to do with those parentheses. Then you can combine some like terms and ultimately solve the equation for x. And that is your ultimate goal. Then we come to the magnificent 7. The 7 figures, 7 solids we've talked about in geometry this year with regards to volume. I provided the volume for you. You need to write the formula, and then what base, width, height, radius, whatever it asks for there, what lengths, what values give you that volume. Math exploration, something relating Fibonacci, Zekendorf, and Lekkerkerker. What a great name. Names, Fibonacci, Zekendorf, and Lekkerkerker. The Fibonacci sequence is a number pattern you may have some familiarity with. Write the first several terms below. You would have studied this more extensively in pre-algebra, but you got some taste of it in your algebra packets. Basically, it's the number system, or the number pattern, that each number in the sequence is the sum of the previous two. So it starts with 1 and 1, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on and so forth. Okay? There are several pretty interesting ways the Fibonacci sequence presents itself in mathematics and in nature, the most notable being the golden ratio. The Fibonacci sequence is also a complete sequence, meaning that every positive integer can be written as a sum of distinct Fibonacci numbers, meaning no numbers will repeat. So your first task, finish this out to the end there. Of course, the sequence goes on beyond that, but that's just where we stop here. And then your task here is write each number below as the sum of distinct Fibonacci numbers. So for example, 16. I might write that as 3 plus 5 plus 8. Okay. Notice I did not repeat any. They are distinct Fibonacci numbers. For 40, do you even have enough numbers written down here to get to 40? I'm not quite sure. Let me go one more out. 8 plus 13 is 21. So let's see. If I do 13 or 21 plus 13, that's 34. I need 6 more, so plus 5 plus 1. That gets me to 40. Distinct Fibonacci numbers, none of them repeat. Then, in 1952, along came Gerrit Leckerkircher. He concluded that, in fact, every positive integer can be written as a sum of distinct Fibonacci numbers without using consecutive ones. He missed out on internal recognition for this conclusion because he didn't prove his result for all cases, which Eduard Zekendorf did in 1972. Thus, Leckerkircher's conclusion is known as the Zekendorf Theorem. Isn't that just, that's cheap. Write each number below as a sum of Fibonacci numbers such that it satisfies the Zekendorf Theorem. If nothing else, you must admit that those are 3 of the coolest names ever. Seriously? Yes, they are. So, what the Zekendorf Theorem says is that every positive integer can be written as a sum of distinct Fibonacci numbers without using consecutive Fibonacci numbers, which I actually did with 40 here, 21, 13, 5, and 1. Notice how in the sequence, 21, 13, 5, and 1, none of them are consecutive. None of them are right next to each other in the sequence. So for 16, 3, 5, and 8, well, they're all consecutive. So how could I rewrite that using Zekendorf's theorem using non-consecutive numbers? How about 3 and 13? Okay. That would satisfy Zekendorf's theorem. So your job with the 5 numbers below there to write each of these as a sum without using consecutive Fibonacci numbers. That would be numbers that appear next to each other in the sequence. And do me a favor, when you get older, start having kids, name one Zekendorf or Leckerkircher. Send me a picture, I'll put up on my wall. All right. Next one, we have mean, median, and mode. Just like in algebra, I'm asking you to create your own set of numbers. I'm asking you to create a set of 11 numbers with a mean of 70, a median of 60, and a mode of both 88 and 50. I was helping someone in algebra with this one, and yeah, there are multiple answers here. I mean, obviously, your sequence or your set must include 88 and 50 at least twice each, making them the mode. I mean, you could potentially have them appear each 3 times, right? As long as both of them are the mode, they appear the most with the same number of times. You know 60's gotta be in there as the median, okay? So even if you only have 88 and 50 each appear twice and 60 once, that's 5 of your 11 numbers already kind of defined for you. Then your other 6 have to make it some way to end up with a mean of 70. So multiple answers, definitely. Okay, but you get to kind of create this one on your own. And then last but not least, the 12 given polynomials. Each one is used once in that figure. Your job is to figure out where they are. So that is math packet number 11. It is due May 4th. If you have any other questions, please feel free to come and see me. And of course, turn in early so you can get not only the bingo square, but the benefit of kind of, knowing how you're doing before it's actually due. So that's how you math. Don't forget to like and subscribe. Thanks for watching and have a great day.